Welcome everybody. Today we are going to be talking about exponential functions, which you've probably studied before in Algebra 1. This might look familiar to you. This is sort of a basic exponential function, or the form of an exponential function, f of x equals a times b to the x power. These also might remind you of geometric sequences, which we'll see a little bit later. So, all right. So yeah, this is the basic form of an exponential function. The defining feature here is that x, or our independent variable, is the exponent in the equation. So this calls an exponential relationship. So what does that look like? Let's just take, a basic example here. Let's just go like f of x equals 2 to the x. Just, what would the table look like? Just so, if you're a little rusty on these, you probably haven't seen these in a couple years. What do these look like? And yeah, let me just put in, -2, -1, 0, 1, 2. I might even go a little further there. All right, let me start with 0. 2 to the 0 power. Anything to the 0 power is actually 1. 2 to the first power, that'd be 2. 2 to the second power, well, that'd be, thinking about that. So if we're plugging in 2 here, 2 to the second power is 4, right? And then 2 to the third power would be 8, okay? Now, it might have been a while since you've seen negative exponents, but one way to think about that, if you look at the pattern of just this column here, these are getting multiplied by 2 each time, which that's what we call, this is sometimes called the base. Okay, if we're talking about exponents, the thing being raised to an exponent is the base. So these are being multiplied by the base every time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Well, in order to continue that pattern backwards, you could think of this as dividing by the base. So this is actually going to be 0.5, and then this is 0.25, or 1/2 and 1/4. So, and seeing it more like this, if I put in, let me just do this one as an example, f of -2, and I put that in, we get 2 to the -2, which is 1/4, or 0.25. Okay, I had to fix some lighting issues there. It was looking a little weird. All right, so yeah, we kind of get this pattern in the output values where they're being multiplied, as opposed to like a linear pattern where what's happening in the output values is there's a certain amount being added or subtracted every time. Here with exponential, there's something being multiplied every time, or you could think of it as it's, in some cases, there's division happening every time, but usually we think of exponential relationships in terms of multiplying. Okay, so that's a basic exponential function, just to kind of jog your memory there on what studied a little bit in Algebra 1 about exponential functions. Now, back to this here. What we usually refer this A as, we call that, like the initial value, or perhaps a starting value, and then B is we could call that the growth rate. Okay, similar to the common ratio when we were studying sequences. So I might call that the common ratio also. We can think of it as that also. All right. And of course, we could also call it the base, like I said earlier. Okay, it's the base of the exponent. All right, so that's your basic exponential function. Now, one other thing that you see with exponentials is, and I finally got my setup here so that I can show my document camera on my computer screen. So here's an exponential that I graphed earlier, and so we have it on the graph. Don't worry about what its equation is right now, and just to kind of see, what does an exponential function look like? So it kind of starts out here, and actually here I might get that off for right now. And then it just kind of swoops up here. Okay, so this is one example of an exponential function. Also, one key feature of any exponential function, it has this line that it approaches and never intersects. And we've studied these before, back when we did rational functions. We have this asymptote here. Okay, we have an asymptote that it sort of, it's a horizontal asymptote, right? It never actually goes past that line. Now, looking at Desmos here, it looks like, well, it looks like it's touching that line. But if we zoom in here, I'm going to just zoom in a lot here, really zoom in even more. We will see eventually, I know it'll happen, there we go, that the line does not actually touch the asymptote. It's just really darn close to it, but never touches it. All right, so we're going to have those with these graphs too. Sorry if I'm making people dizzy. Um, yeah, with this rapid zooming in and out here. All right, so yeah, that is called an asymptote. We've studied that before, so I don't think I need to say anything else about that. All right, so let's just use Desmos here to do a little bit of exploration. So I'm going to go ahead and get rid of these for now. And let's just graph, really basic exponential. Let's just do f of x equals 2 to the x. Now, if you want to follow along with me on Desmos, that'd be great, or you can just watch here. But it's always nice. I feel like more learning happens if it's hands-on, you do it with me. So I'd really recommend, you pull up a window and do this in Desmos with me. All right. So here's what 2 to the x looks like. We can also, in Desmos, I don't know if I've shown you this before or not, but you can have a table created from this also if you want to take a look at some actual numbers here and see. And this is the same table I actually did on the example on paper, okay? Also, if you want to extend it here, you can. You can just go in the last column here, or the last row rather, and then hit enter, and Desmos will just kind of create the table for you, so you can kind of see what's happening with the numbers. All right, so there's what 2 to the x looks like. All right, we might come back to that later. I'm going to go ahead and get rid of the table just because I don't want this to get too messy here. And then I'm just going to turn off the 2 to the x for now. Let me do another function. Let me call this one g of x. And let me just change the base, just see what happens here. Let me go, let's just do 10. Actually, let's do a fraction here. Let's go 1/2 to the x power and just see what that looks like. Oh, interesting. Okay, so if we have a base that maybe it's a fraction, it goes like this. We'll kind of talk more about later maybe what values here of the base or the growth rate, what causes the exponential to decrease like this, all right? All right, so that's interesting. We can compare those two, say they kind of look like that together, all right? And let's go ahead and throw another one in there. Let's do a larger base. Let's go like 10 to the x. And let's compare that to 2 to the x, just see. So yeah, you can just see that makes sense. The one with the higher base increases more quickly here, okay? A little bit of funkiness here in the negatives, okay? But overall, when we're looking at positive inputs, you can see that 10 to the x definitely increases much more quickly here. Okay. All right, so earlier I gave you this equation, this form of an exponential. That's sort of the formula you probably used in Algebra 1. Maybe it went a little bit beyond that. But now we're going to be talking about transformations of exponential functions, okay? So that form looks a little bit different here. And we're going to call this g of x. And so it'll look like a times b to the x minus h plus k. This might look a little familiar to you, okay? So we see those h and k variables like we've seen throughout the year in these equations, and we've been talking about transformations, all right? So, and these cause the same transformations as they always have. A, if it's, if A is bigger than 1, it causes a vertical stretch, right? If it's less than 1, it's a vertical compression. Um, and then if we, let's see, H here, that causes a shift left or right. Okay, so that causes the graph to go left or right, and it's the opposite you might think, right? We've talked about in the past, H lies, K tells the truth, right? Has to do with the minus there. And then K causes an up or down shift, okay? The other thing, if A is, less than 0, okay, you get a reflection over the x-axis, right? So let's take a look at Desmos again. So let's put in f of x equals, and we'll go back to good old 2 to the x here. And let's actually add some transformations in and just, see what happens. This is, something that again, you've seen all year, but just let's see what it looks like for exponentials. Let's change, right now the a value is 1. Let's first just change the h value. And just for, actually, I might just call this something else here. You'll see why in just a second. Let me just write down our transformation form here. Oops. Come on. Oh, yeah, I got to use parentheses here. Okay, so just so we have that handy, all right, we're not going to worry about that warning there. Okay, so we have, a times b to the x minus h plus k. So let's say we want to change h to something here. And I think in Desmos it just has this quirk where you have to put the exponent in parentheses. All right, so we'll go like x minus 2. So notice what that did. It shifted over. Um, here's f of x, the reddish orange one here. And h of x is shifted 2 to the right. You can see every single point is 2 to the right, all right? And then, of course, if this was like positive 2, it's shifted 2 to the left, 2 to the left, all right? All right, and then let's get rid of that for now. I'll go ahead and leave the parentheses there. And let's see if we put in like plus 5. Yep, gets shifted up by 5 here, shifted up by 5. If I want minus 5, it gets shifted down by 5. So the same transformations you've seen all year. What if we put in a stretch value? Let's go ahead and just put in like, I don't know, 3 times 2 to the x. So, so if we're looking, and let's actually create the tables here, and I just want to show you what do the tables look like. All right, so you'll notice looking at the tables, well, the x values are the same, but how are the y values different here? Oh, well, 0.25, 0.75, that's off by a factor of 3, right? 0.5 times 3 is 1.5. 1 times 3 is 3. 2 times 3 is 6, etc. All right, so basically all the y values get multiplied by 3. So, and when we graph these, a handy reference point to use is 0, 1. That's on every single parent. This would be our parent graph here. I should have mentioned that earlier. So every parent graph is going to have a 0, 1 point on it, okay? And then the other reference point that it's always going to have on it is 1 and whatever the base is. So let's go ahead and write that down on paper. That's going to be a handy thing for you to remember when you do the assignment. So let me switch back over to this, and let's write that down. That seems to be an important piece of information. So use these reference points. 0, 1, and 1, and then it's always the base, right, is the other reference point. So what letter, what variable do we use for the base? Well, that's b. So 0, 1, and 1b, okay? And so how you can graph these then is you can just use those two reference points and just basically apply the transformations. So like, let's think about this one, and again, I might just kind of switch over to paper and then come back to Desmos to verify this, okay? So let's say, let me get a new piece of paper here. I'm being asked to graph g of x equals, and we'll just make up a new one here, like 5 times 2 to the x. We'll just do that for right now, okay? So what you could do is, the parent function. The parent function is always going to be just the base to the x power. This is a little bit different than we've seen in the past. There are different parent functions for different exponentials. So the 2 is not a transformation parameter, okay? It's not involved with AH or K. It's actually part of the parent. So you have to think about what is the parent function. There's going to be a lot of different parent functions with these graphs that we do, okay? So, all right, and so that means our reference points are going to be 0, 1, and then 1, and then 2, because this is 2, right? Okay, so then how does our, what points would we have on the transformed? So points on g of points on g of x. Well, what's going to happen here is we're still going to have 0 and 1 here as our x values. And then how these change, well, if this is it's a vertical stretch by 5, right? So all the y values are going to get multiplied by 5. So we should have a 0, 5 on g of x, and then we should have a 1, 10. All right, so that can help us graph this then. We know it's going to go through 0, 5, and 1, 10. All right, so let's go back to Desmos. And of course, we'll have Desmos to help us out here, right? If we were doing this in person, I might do this a little bit differently, rely a little less on Desmos, but hey, that's all right. Okay, so let me go ahead and put in that graph 5 times 2 to the x. I just want to prove to you guys that those points are, in fact, on this graph. So yes, we do have 0, 5, and then we have 1, 10 there, which I can't have it stay. Okay, so there we go. So 1, 10 is also on the graph. All right, so that is one approach to graphing these transformed functions. Okay, what's the domain and range? Let's shift over to what domain and range is for these. So, and let's go ahead for right now. We'll write it in interval notation, which we've been doing all year. I will warn you on the assignment, it's using a slightly different type of notation. It's very related to inequality notation. It's slightly different, but we'll get into that after I talk about this. Okay, so yeah, let's do interval notation first. Domain on these, it's always going to be negative infinity to infinity unless there's some kind of context or something. But there's no context here, so yeah, it's just negative infinity to infinity. Range, we have an asymptote here at y equals 0, right? Or the x-axis is the asymptote. So the range, it's not going to go below 0, and it's going to go up to infinity. Does it actually touch 0? No, it doesn't. It never actually touches 0. So we do use a parenthesis here instead of a bracket. Okay, now how do you write this in inequality notation? Just a little review, because this is what the website likes to use. If it's been a while since you've used inequality notation, that's how you would write that. One way to write this would be like this. However, there's a simpler way to write this. If you think about what y could be here, yeah, sure, it could be between 0 and infinity, but a simpler way to write this would actually just be y is greater than 0. Okay, if you think about it, this means y is greater than 0. That implies it could go to infinity. Okay, so I'll just warn you that the website prefers this simplified way of writing this. All right, now I'll go ahead and show a problem on the website. Let's just do that now, because there are just a couple of nuances on my.hrw.com. All right, so here's number 1 on the assignment here. So it says select the correct graph of the parent function as transformation, then determine the domain, range, and y-intercept of each function. All right, so we have a to the x and is the parent function, and then the transformed function is 8 to the x minus 7. So first of all, I want to find a graph where it looks like the graph has been moved down by 7, right? We'd have um, a shift down by 7. So it looks like B is going to be our right answer. Yeah, well, actually, no, I'm sorry. It could be D here. This would not be correct because this is a reflection, right? Both of them are being reflected, so that would make sense. All right, so it would be, yeah, it would have to be D here. These are shifted up, both A and C here, and this one's shifted down, which would make sense because it's minus. All right, so D. So g of x is a shift down by 7. So we're going to say downward by 7. You don't have to worry about putting a negative in here. Okay, you just leave that as it's always going to be positive here. This kind of is referring to the sign in a way. Okay, the domain. Now, this is the funky thing I was talking about. It's got this weird like curly bracket and then this looks like an absolute value symbol. It's just a slightly different way. It's called set notation. It's a way to write, one way to write domain and range. But really, all you have to worry about is inequality notation, which you probably used well in this class and also in Algebra 1. So don't worry about that too much. Just select the correct inequality here. So the domain of f of x, well, it's just right here. Well, it goes all the way to negative infinity, and then it's going to keep going to positive infinity. It's going mainly upward, but it is going to continue going to the right forever. So we go negative infinity to infinity, all right? The range of f of x, this is the parent, remember. Well, it starts here at 0, right? We're thinking y values here, so it doesn't go below 0, and then it goes up to infinity. So we'd say 0 to infinity, or remember I said the simpler way to write that is just y is greater than 0. Okay. G of x, well, this is going to have the same domain. It's also going all the way left, all the way right. All of these exponentials are going to have that as the domain, unless there's some kind of context, some kind of story going along with the problem. The range, well, it looks like it goes down to -7, which would make sense because that was the shift downward. So it's going to be all y values greater than -7. So that would be the most simple way to write that is y is greater than -7. All right, now we do have to identify the y-intercepts also. A couple different ways you could do that. You can graph these both on Desmos and identify the y-intercept. What I might do, I might just kind of quickly do it on paper because it's, to me, a little easier, but it's up to you how you want to do that. So uh, you can just put in 0 into the function. So if you want to find y-intercept, you can just put in 0. So that means 0, 1 is the y-intercept of the parent, which in fact all parents are going to have that as their y-intercept. Okay, wait, remember that's one of the reference points. In fact, okay, so let's answer that one. Yeah, 0, 1. Okay, g of x. Let's go up to that and just think about. Now, this is just one way to do it. You could possibly think, well, I can think of a shortcut here, Mr. Anders. Can I do it that way? Sure, if you think your shortcut works, do it that way. I'm just showing you one way. So 8 to the 0 minus 7, well, this would just be 1 minus 7 would be -6. So 0, -6 is the y-intercept for g of x. All right, so let's put that in here. And let's see if I got my answer right. Yay, I did. All right, so that's how those work.